Hello, everyone. So last time we started our discussion on the isolation method of determining the reaction rate law or the rate law of a reaction. Okay, so we said how you can use this. Say, if you consider what we have here. Okay, if you have a reaction that has two reactants, so like A plus B give us a product P, we say that for you to write the rate law of this reaction, you need to know the order of the reaction with respect to each reactant. Okay. So how you can do that experimentally is making one of the reactants to be in excess. So when one is in excess, the other one is in a low concentration. So the order you'll be able to get for that will be the order with respect to the dilute reactant or the low concentrated reactant. And you can swap between the two to find now the order of the reaction with respect to the other reactant. So today I want us to look at an example. And I gave you this example where you're supposed to use the isolation method. So you have this reaction of NO with the chlorine gas to give us this product. So if you are to generally write the rate law of this particular reaction, a rate would be given to us the rate constant K times the concentration of NO, say to power M, times the concentration of chlorine to power N. So the reason why we use this isolation method, we want to find the values of M and the value of N, okay, to find the order of the reaction with respect to each reactant. So we have two sets of data here. The first, we are told that in one experiment, the initial concentration of NO is 0.1 molar, okay, and that of chlorine is 2.0 times 10 to the power minus 3 molar. So if you compare the two reactants, you notice that the one for NO is much higher than that of chlorine. So therefore, the one for NO remains constant, considered to remain constant. And the one that whose concentration is monitored is chlorine. So this one is monitored with time, and this is the data that we have here. So this experiment helps us to find the order of the reaction with respect to chlorine. Okay. And then there's a second set of data, or there's a second experiment where the initial concentration of NO is 1.0 times 10 to the power minus 3 moles per liter or molar, and that of chlorine is 0.150 molar. Okay, so here when you compare the two concentrations, again here you notice that for chlorine is much higher compared to that of NO. So it is in excess. So therefore it is considered to remain constant, and the concentration that is monitored now is that of NO. the change in the concentration is monitored with time. Okay, so this one will help us determine the order of the reaction with the respect to NO. Now, so we're supposed to determine the form of the rate law, okay? Form of the rate law, and also the value of the rate constant. When we come to our rate here, we're supposed to find the form of this expression, find the value of M and N, and also find the value of the rate constant. Okay? So for us to do that, we make certain assumptions. We assume, for example, we want to find, when you want to establish the order with the respect to chlorine, using the data of experiment 1, we assume, say we assume that it is first order or second order or third order with the respect to chlorine, and then we use the expressions for those orders and try to see if our data set, our experimental data, fits to a certain expression. So if it fits with first order, then we would say it is a first order reaction. If it fits with second order, then it is a second order reaction, and so on and so forth. Okay. So the first assumption we make for the first experiment, we make an assumption. We assume that the reaction is first order with respect to chlorine. Okay. And this will help us to determine the value of the rate constant. That is K prime, okay, using the first order kinetics. Now, one thing I need to mention here, this is written K prime because it is the corrected constant. So remember, here we have isolated chlorine. So that means rate, yeah, which was given as K times the concentration of NO, okay, may say to power M times the concentration of chlorine, okay, it changes because now that of NO is constant. So we assume that this particular term in this expression is K prime, okay? So we are able to determine K prime from this, okay? Because the corrected rate law now from the isolation becomes this, okay? Power N, that is K prime times the concentration of chlorine to power N, okay? So we assume that N equals to 1. That is why that's what it means when you say we assume that it is first order. So we can determine the value of K prime using that expression. So when we assume it is first order, then the first order integrated rate law applies, okay, which can be written as this: natural log of A at T equals to natural log of concentration of A naught minus KT, okay, which can also be written as this expression here, okay, which is natural log of AT over A naught equals to minus K prime T. So now, say if we use this expression here, we consider our data set. So we consider the concentration at time equals to 1 hour, which is 3600 seconds. So when we consider the corresponding concentration, the concentration at 1 hour is 1.17 times 10 to the power minus 3. And the initial concentration is 2.0 times 10 to the power minus 3. So equals to minus K prime T, and T is 3600 seconds. So if you put in our values there and you make K prime the subject, you can confirm this using your calculators. You find that K prime equals to 1.5 times 10 to power minus 4 per second. Okay. So that is using the initial concentration of chlorine and the concentration at T equals to 1 hour. We can, for us to find out if this is actually a first order, we try the second data set where we consider at time T equals to 2.5 hours, okay? And find out what do we get as the value of K prime, okay? So there we use the corresponding concentration at T equals to 2.5 hours, which is given as 5.18 times 10 to the power minus 4, okay? Divide by 2.0 times 10 to the power minus 3. That is the initial concentration, equals to minus K prime times the time, which is in seconds, to be 3600 seconds times 2.5 hours. Okay, 600 seconds per hour times 2.5 hours. So again, you can confirm this calculation of K prime. Find that K prime equals to 1.6 times 10 to the power minus 4 per second. Okay. So when you compare the two values, this is 1.6 times 10 to the power minus 4 per second. And the first one was 1.5 times 10 to the power minus 4 per second. So you see that the two values are close. Okay, they're very close. So you see that the slight difference in the K prime values can be maybe as a result of rounding off in the calculation. Otherwise, the reaction would be second order. So for us to rule out that this particular reaction is second order with respect to chlorine, we assume second order, okay? If you assume that it is second order with respect to chlorine, then we apply the second order expression using our data set, okay? So making this assumption, assuming that the reaction is second order with respect to chlorine, this expression would apply for second order, for a second order reaction, okay? So this one is 1 over the concentration of chlorine at time T minus 1 over the concentration of chlorine at the initial time equals to K2 prime T, okay? So again, we use our data set. We use the initial concentration, that is the concentration at T equals to 0. And then we use the concentration at T equals to 1 hour and see how it fits. So this is the concentration at T equals to 1 hour, and this is the initial concentration, or at T equals to 0. So if we put in the values after 1 hour, that is 600 seconds. If you make K2 prime the subject, then you get the value of K2 prime to be equals to 9.85 times 10 to the power minus 2 liter per mole per second. Okay, so that's the first value. Then we also use the data for the T equals to 0 and T equals to 2.5 hours and find out what is the value of K2 prime we get. So if you check this, find that this here is the concentration at T equals to 2.5 hours, okay? And this is the initial concentration, okay? And this is the time in seconds after 2.5 hours. So if you put in those values and make K2 prime the subject, can confirm this. The value of K2 prime you get is 1.59 times 10 to the power minus 1 liter per mole per second. Okay? So if you compare the two values, okay, you notice that they are very different. So they differ almost by a factor of 2, which means they are too far. So then this reaction cannot be second order. Otherwise, we would have gotten similar or close enough values for K2 prime. So therefore, because for first order, we found that the K prime value that we got was very close. So we can say that this particular reaction is first order with respect to chlorine. So therefore, N equals to 1. So it is first order with respect to chlorine. So now we need to find the order of the reaction with respect to NO. And that was the purpose of the second experiment. The data that we got for the second experiment would apply in this case. So using the second data set, we use that to determine the order with respect to NO. So we can start by making the assumption that it is second order with respect to NO. So we assume that M equals to 2. So then we apply the second order expression for this particular reaction, or for NO. Okay, so the expression would be 1 over N, concentration of NO at time T, minus 1 over the concentration of NO at T equals to 0, equals to K2 prime T. Okay. So we have all these values, the concentration of NO at, I think after 30 hours, T equals to 30 hours, okay, is 1.1 times 10 to the power minus 3. And the concentration of NO at time 0, at time T equals to 0, is 1.5 times 10 to the power minus 3. So this equals to K2 prime times T. So here we are changing the time into seconds. Okay? So 30 hours times 3600 seconds per hour. Okay? The hours would cancel out and you remain with your second. Making K2 prime the subject, we find that K2 prime equals to 2.24 times 10 to the power minus 3 liter per mole per second. Okay, so that is using one set of data for the NO experiment. And then now we consider the values of concentration at T equals to 0 and T equals to 100 hours. And then we use our expression, second order expression, and find out what value of K2 prime we get. So the concentration of NO at 100 hours is 6.79 times 10 to the power minus 4. And the initial concentration remains the same, that is 1.50 times 10 to the power minus 3. Okay, so this equals to K2 prime times 100 hours times 3600 seconds per hour. Okay, so again, when you make K2 prime the subject, you can confirm this. K2 prime is found to be equal to 2.24 times 10 to the power minus 3 liter per mole per second. Okay. So now if you look at the two values of K2 prime that we're getting, they're actually the same. Okay. Which means that this particular experiment confirms that this particular reaction is second order with the respect to NO. So therefore, our reaction or our rate law expression becomes, so our rate law expression becomes rate equals to K times concentration of NO squared. So remember, it is second order with respect to NO, and it is first order with respect to chlorine. So this gives us the rate law of the reaction. Now, the second part of this problem is we need to find the value of K. Okay, so you have to remember we had said that rate equals to K. So now this is K NO squared times the concentration of chlorine. Okay. Now, in the first instance, where the concentration of NO is kept constant, okay. So now here in the first experiment, so we are finding the order of the reaction with respect to chlorine. Okay. This concentration of NO is constant. So then the expression would be rate is given by K times the concentration, the initial concentration of NO squared times the concentration of chlorine. Okay, so this particular this term here, K times that is the rate constant times the initial concentration of NO squared, gives us the K prime. Okay, and we have the value of K prime. And so since we have the value of K prime and also the value of the initial concentration of NO for the first experiment, we can be able to find the value of the rate constant K. Okay, so that is using the first experiment, but also using the second experiment, which was meant to find the order of the reaction with the respect to NO. Okay, so in that case, a rate, okay, the concentration of chlorine is kept constant. So rate would be equal to K times the initial concentration of chlorine, okay, which is this, power 1 times the concentration of NO squared. Okay, so in this case, since this concentration is constant, then this particular term in this expression, it represents K2 double prime. Yeah. Okay. So since we know the value of K2 double prime and we know the initial concentration of chlorine, we can be able to find the value of K. So you see here that the two experiments can help us to determine the value of K. Or that is the rate constant. So using the second experiment, because the second experiment, you see that K2 prime, we are getting a very accurate value for K2 prime, K2 double prime. Okay, so therefore we can use this second experiment to find the value of the rate constant. So you find for that second experiment, as I've said, rate is given by this expression. And then considering that the concentration of chlorine is constant, then rate equals to K2 double prime times the concentration of NO squared. Okay. So K, you remember what K2 double prime represents. In this case, K2 double prime represents K, that is the rate constant, times the initial concentration of chlorine. Okay. So therefore, K is going to be given by K2 double prime divided by the initial concentration of chlorine. So in this case, we have these two values. K2 double prime has been determined as this, that is 2.24 times 10 to the power minus 3 liter per mole per second, divided by the initial concentration of chlorine, which is given, that is 0.150 moles per liter. So when you do that, then you get the value of K to be equal to 1.49 times 10 to the power minus 2 liter squared per mole squared per second. Okay. We could also use the first experiment, of course, to determine the value of the rate constant K. Although it has to be pointed out that because the two values of K prime that we found were not exactly the same, but they are close enough. So there's lower precision for that particular value of rate constant that we get. So if we use the first experiment, K is given by this. It is K equals to K prime divided by the concentration of NO squared, NO, the initial concentration of NO squared. So all these are given. So you can say 1.6 times 10 to the power minus 4 per second divided by the initial concentration of NO squared, that is 1.10 times 10 squared. Okay, I don't know if this is correct. The initial concentration of NO is 1.5 times 10 to the power minus 3. No, this is the second one. So this one is 0.1 molar. Okay, so you have to make sure that you use the correct one there. Has to be 0.1 molar squared. Okay. So if you do that, you get the value of K to be equals to 1.6 times 10 to the power minus 2 liter squared per mole squared per second. Okay. So if you compare the two values, you notice that there's a difference, but then we would go with this one. They are close, yes, but then the first one is more accurate using the K2 double prime value, which is really precise. Okay, so that is how you apply. So therefore, if we use this particular rate constant value, then rate, that is now the exact expression, rate law expression, the rate equals to 1.49, okay, times 10 to the power minus 2 liter squared per mole squared per second. Okay, then times the concentration of NO squared times the concentration of chlorine to power 1. Okay, so this is the exact rate law now of this particular reaction that you will find based on the isolation method.